Okay, so we are on to week 6 today, which is going to be a pretty big shift in the focus. We'll still talk about a lot of the looping things we talked about before, but we're mostly going to be focusing on writing functions now. So we will talk a bit about using the functions that we write within loops, but the focus is mostly going to be on writing functions, okay? We're going to talk about functions today and on Wednesday. And then on Monday, we're going to have a lab. So it's like sort of the odd Monday lab. That'll be the last lab that we have for this class. And then, of course, you have your final project and the midterm. In regards to the midterm, it is due on Wednesday, technically. If you need more time, of course, you can have it. Just let me know. The other thing I wanted to mention is if you have questions on it, I'm more than happy to answer them. And if you would like to set up a meeting with me with your entire group to talk about things that you're confused on, I'd be happy to do that too. I can meet with you individually if you'd like, but I'd probably prefer to meet with your entire group if you'd like to do that. Okay, so even though it says midterm, it's really not any different than the homeworks that we've had in the past. Okay, so I'm happy to answer questions. If you want to meet, we can do that too. Okay, how's it going with the midterm? Are there any questions anybody has right now, or are you feeling okay?
I had a question. I don't know if you can answer this, but when I ran the estimate V models, it didn't run for all of the districts. I'm assuming that was intentional. Okay.
Yeah, I think that's fine. It is probably related to something. So I think it might be that I asked. That doesn't work apparently. I think somewhere, didn't I ask you to only limit it to schools that had data on both of these groups?
So that was even like the districts where the models didn't run. I looked at the counts and like it didn't really look like there was a reason that it shouldn't run. So it was like after we filled, like they had full data, it just didn't run for some reason.
Oh, did you just get warnings or was it?
Yeah, I got warnings and then the estimate V output was null, or there were like 0 rows. Yeah.
All right. I will double check on that, but I don't think that's anything you have to worry about.
Okay, I just filtered them out anyways.
Yeah, that's fine.
Yeah.
I'll double check on that, but because it's been like 2 years since I wrote this really. But I don't think that's really a problem.
Okay.
So any other questions? Okay. I have a kitten attacking my foot. Here. Okay. On to class stuff. So writing functions, as I mentioned. So the agenda for today, the first thing that I want to cover is sort of this idea that everything is a function. Okay, this is one thing that makes R a little bit different than some other languages, is literally just about everything that happens in R is a function. Okay, so this is sort of just like background, but I want you to think about that because it sort of helps shape the way that R works generally. Okay, then we'll talk about the components of a function and sort of function workflows, how to write functions and some things that you might want to consider when you're writing functions. And we'll actually practice writing a couple functions as well, or at least one. So the main learning objectives, I would like you to understand and be able to refer to the 3 main components of a function. Okay, there's really 2 that matter a lot, and then the third matters a lot less until you get into more complicated stuff. So we'll mostly focus on 2 of the 3. Okay, understand workflows that lead to writing functions. So you're not always going to be writing functions. If you just need to do a task one time, you can just write the code to do that task. When you really should be writing a function is when you're doing a task repetitively and you need to do it over and over again. And so therefore, writing a function can be really helpful. Okay, and then hopefully by the end, you'll feel comfortable writing at least a few basic functions. Okay, and that includes just replicating things that we can already do in base R. So like maybe we can write a function to compute the mean, right? We could just use mean, or we could write our own function to do it that maybe does something like removes missing data by default. Okay. All right, so functions, right? As I said, everything in R is a function. That includes things like plus, right? Goodness, oh boy. So this is how we would typically write this, right? 3 plus 5, and we get some output 8. But plus is a function. It's what's referred to as an infix function, which means it's a function that sort of goes between its two arguments, okay? So we could rewrite this, though, so it looks more like a regular function that we're used to in R. So typically, when we think of things like mean, right, or something like that, we have the name of the function, and then we have the parentheses, right? So we could actually write this function like that, too. Any idea on how? Any thoughts? I'll just show you. It's like this, okay? This looks bizarre, but the reason that we're doing this is because we have to wrap the function in backticks, okay? Because it's sort of a reserved function, okay? So this is like an illegal name for a function generally. So we can wrap that in backticks, and then we have our parentheses saying this thing is our function, and then we just provide it the two arguments to our function, 3 and 5, and it will add them together, okay? So we get the same output. So what about this? If 3 plus 5 looks like this, take a minute and just see if you can rewrite this same code using this sort of a notation to get the output here. What do you think that's going to be? All right. Do we need more time?
I'm going to be honest, I didn't hear what you asked us to do, and then I didn't do it. So
that's all right. I asked you to rewrite this to get this output using this sort of an approach. Okay, so this is how we would do it. It looks bizarre, but it makes sense if you can think through it, right? First, we're going to apply the function plus and add 3 and 5. That's going to give us some result, and we're going to add 7 to that result. Okay? And that's 15. Or we could use Magritter and we could do something like this, right? Plus 3 and 5, and then pass that to 7. Okay? So this is, and actually sort of, not really important, but sort of. I have this inside of here that, right, this is 3 plus 5 plus 7. This is adding 3 and 5 first, and then it's adding the result to 7, just like this, right? 3 plus, because it'll evaluate left to right. 3 plus 5 plus 7. So this is actually done in the same order as this. And this Magritter makes it a little more clear what's going on there, maybe. So again, this is not really that important in terms of, I wouldn't expect you to ever write plus like this. But it is important in terms of thinking through everything being a function, right? And everything can be written like normal functions are, like this, with the parentheses and then arguments within the parentheses, okay? So this is pretty clear, right? We have a function plus, which takes 2 arguments, and it adds them together. That's all it does, right? And those arguments both have to be numeric. Okay. These are also the same. Okay. This, except what's being assigned. Normally, we would assign A to 7 like this, but we can also do it just like this, right? We surround the arrow pointer in backticks, and we say A and 5, and then A is 5. Okay, the only reason I changed what they are called is, or what the value is just so that you can see that A actually changes, right? So this is, again, sort of odd, but it works because everything that's happening in R is a function. So we can think of them all just like normal functions. Okay, this, though, does lead to some potential devious behavior that you could have. All right, so what if we wanted to redefine the plus operator? Right, this is not something I would recommend you ever do, but if there's somebody you really don't like and they're working with R, you could go and run this in their console and then delete it and then run away and see how fun their life is from there. So this is redefining the plus operator so that it's a function x and y, and we just randomly sample one value from a random uniform distribution. If that value is less than 0.01, then we multiply the result of our sum by -1. Otherwise, we just sum them. Okay, so then if we say, okay, 1 to 500, 1 to 500, we're going to add those together a bunch of times. We get 5 times that it's less than 0, right? And then here, now I say, okay, remove that thing and then do this, and we get, oh, looks like my plus might not have actually removed, because that should be 500. That's a little concerning. Well, we'll see what happens with the rest of these slides. But the point is, right, this is a little bit scary because now somebody could use plus expecting the plus to work like it normally does, but we've redefined what that function is so that it randomly, every once in a while, flips the sign. Okay. All right. Functions are also usually objects. Okay. So here's an example, right? LM for fitting linear models, right? We've used this quite a few times now in this class. It's for fitting linear regression models, right? And all I'm doing here is I'm creating a new object, which I'm calling A, and I'm defining that as LM. Okay. Now I can call A as my function, and it works just exactly like the LM function because I've just created a new object called A that has the contents of the LM function. So A is now also the LM function. Okay, does that make sense? So what does this all mean? Anything that does anything in R is a function. Okay, that's sort of the big take-home message. Anything that does anything. And there's obviously lots of things that happen in R, and they're all functions. Okay, functions are also generally, but not always, stored in an object, and this is also known as being bound to a name. Okay, the function is bound to a name. I say not always because often we want to use anonymous functions. Okay, most often this happens through loops, and we've been doing this actually quite a few times already. Okay, so for example, if I wanted to loop through something and compute the mean, I would pass the function mean, and that function is bound to the name mean. Okay, but if I want to do additional things, I could write another function that does those additional things, or I could just include those arguments within my loop. And basically, I'm writing a small little function right in the loop, and that function only exists for the time that the loop runs, and then it goes away. Okay, so it's never bound to a name. So that, therefore, it's an anonymous function. Okay, here's an example. Using vapply, I'm going to loop through empty cars, apply this function x, right? So here I am defining a function x where I'm going to count the length of the unique elements in x, okay? Where x just becomes a placeholder for the column. And I get this in return. So if I wanted to just compute the mean, right, I could just say mean here, or instead I can create an anonymous function where I'm writing this function here, And that is writing a function, right? It's just an anonymous function that's not bound to a name, and it exists within the loop and then never again. Okay? Is that clear? Questions on that? Okay. Another possibility, if you have a lot of functions that you want to use, you might consider storing the functions within a list. Okay? Then you can access those functions in the same way that you would access a list. So this is a little bit weird, but it's again, there are times I've done this, but like specifically if there's multiple models that I want to fit that are like comparison models, right? I might create a list of different models, model specifications basically, and then I would loop those list of models through a list of data sets, okay? But here's a more simple example where I'm creating a list called funds, okay? That list has 4 objects, quarter, half, double, and quadruple, and each of those are just functions that take one argument, x, and it does whatever the name of it says, right? So quarter is going to take x, some generic vector, and it's going to divide it by 4. Half is going to take x and divide it by 2. Double is going to multiply by 2, and then quadruple is going to multiply by 4. Okay? So these are 4 different functions. They're all very simple functions. This is kind of weird, though, right? This is not like something you will generally see out there. But again, I'm showing you for 2 reasons. One, I think it actually is a neat thing to do. And as I said, I've done it before. But more than that, it's to get you thinking about what a function is. And it's really not different than anything else that exists in R. And that those functions can be stored in lists because lists are super flexible, right? So then we can do things like this. Funds $quarter, right? So that's just going to index this list and give us the object quarter, right? That is now a function, right? We have a function in there, quarter, and so then we have to pass it with parentheses and give it the argument. So we say 100, right? X was our argument, so 100 gets inserted for X, and we have 100 divided by 4, and we get 25. Okay. We could also index the list differently. So I say funds double bracket half, right? So double bracket and then half. That's going to give me this one. And then I can give it parentheses and an argument, 100, and it'll give me 50, right? And then similarly, I could do funds double bracket 4 to give me quadruple, and then parentheses 100, that'll give me 400. Okay? Does that make sense?
I have a question.
Mm-hmm.
Some packages do like wrapper functions that like somehow relate to another function that is like a specific instance of this general function. Is this what they're doing, or are they indexing it in a different way?
It really depends. So a wrapper function is actually the entire tidyverse. You could consider the entire tidyverse a wrapper function because it wraps base functions to do functionality that base can already do. Sometimes wrapper functions are to make the interface easier. So like map2 or pmap, for instance, those are much simpler interfaces than the base versions, which is either mapply or map with a capital M, right? So that's an example where you're basically taking something that already exists and you're making it a simpler version. And specifically, if you want to then simplify it down to like an atomic vector, then it's going to be quite a bit simpler to have that wrapper function. But in other instances, it might be a wrapper function in terms of taking multiple existing sort of functionalities and just sort of combining them. So sometimes there's things like this that will happen, but it just really depends. It depends on what the function is and what they're trying to do.
Thanks.
Mm-hmm. Any other questions? Okay, So what does this imply? If we can store functions in a list, well, then we can loop through that list just like any other, right? So that means we can do things like this. Okay, I'm creating a list here. I'm calling summary. And this is going to be a list that takes these different arguments, these different objects, right? These different elements of the list. And what this is each of these are just functions. Okay, so n is going to be equal to the length. N miss is going to be equal to function s. X sum is .na x. Okay, so it's going to sum the missing data, right? And valid is going to be the same thing except reverse. So it's going to sum the not missing data. And then mean is just going to be the mean, and SD is going to be SD. Okay, I could also write these things all, so I could say function x length of x, right? But I don't actually have to, because just like I took lm and defined it into an object called a, and then a worked as if it was lm, I'm doing the same thing here. I'm just storing the function length in this element of the list, which I'm calling n. Okay? So then I can do things like this. Map double summary. I'm going to loop through that summary object, this object, right? And I'm going to say dot x parentheses. So basically apply the function, each function from the list to mtcars mpg. Okay? And what I get in return is this atomic vector, and it's named because my list was named, and it has the n, the number of missing, the number valid, the mean, and the standard deviation. Okay? You do have to be careful, though. This does not work. Any idea why this does not work? This is why. Okay? The way that map works is it takes an atomic vector and then a function, and then it wraps each element of that thing in the function. Okay? In this case, the atomic vector that we're passing it has the functions, and then we're trying to say apply each of these functions to one vector, right? So if I do this, that works because I'm saying each element of the list needs to be a function that I'm applying to mtcars mpg. Otherwise, it's trying to take it's trying to see this as the function, right? This vector, this miles per gallon vector, it's seeing that as the function, which it's trying to wrap around each element of summary. And we want it to do basically the reverse, so that's why we have to specify this syntax directly like that. Is that clear? So this is like sort of a little bit backwards from what we've been doing. What if we wanted this for all columns? We could use mapdf. What I'm going to ask you to do now, and I know this is challenging, and if you don't get it, that's fine, but I would like you to at least try to extend the previous looping, okay, so that it will take a data frame and it'll loop through the entire data frame and give you that summary back for each column of the data frame. Okay, so basically you're going to grab this and then you're going to try to do something like this, but have it loop through every column of the data frame. Okay, so I'll give you 5 minutes, try your best, and if you don't get through, that's okay. All right, there's the answer, but we'll try not to look at that. Okay. Give me a thumbs up if you were successful. Or something else if you were not. Okay. All right. So that's actually pretty much what I would have expected. This was tough, but we can actually do this by doing something like this, okay? So we have empty cars, mapdf, right? I'm calling mapdf because I want to return a data frame. I'm going to loop through empty cars, and I could use the tilde, but I think in this case, it's actually easier to just say function call. So call is a placeholder for the column, right? Then I'm going to map df through summary, and I'm going to say .x apply each function to each call, right? And then I say .id equals column, and here is my column, and here's all the rest of the stuff. Okay, so this is fairly complicated. It's pretty tricky to get through, right? But it's also a pretty small amount of code, and it's a pretty powerful framework, right? Because with just a little bit of code, we've now looped through every single column and applied multiple functions to each of those columns. Okay? Does this make sense even if you weren't able to write it yourself? Do you understand looking at it how that works? And if not, please ask questions.
I don't understand why this doesn't kick an error for the column that's a character.
Is there a character column in empty cars? I don't think there is. MPG cell displacement HP.
Okay, maybe there's not. I thought there was.
Yeah,
The name of the, oh, those are named rows. That's not actually a column.
Correct.
I was like trying to do some weird if-else statement.
Oh yeah.
Okay, cool.
Yeah,
Thank
I
you.
used empty cars specifically because it doesn't have any non-numeric columns. Any other thoughts on this?
I'm kind of confused about the use of function call in it. Just how does it work? How does it know that it's pulling from the columns?
Yeah, so whenever we're doing map, right, any sort of map function, we can always do function and then name this thing whatever we want it to be for the placeholder for the thing we're looping through. So when I say empty cars, mapdf on empty cars, I could use the tilde and .x, right? But in this case, because I'm doing a double loop, I think that's more confusing. So because what we would end up doing then is we would have tilde here to replace that, and then another .x right there, right? So that would be kind of confusing, I think. Alternatively, we can always write function, and then we can put any name here. We could write x, we could write y, we could write z, we could write anything. So I use call just because the thing I'm looping through is empty cars. So each loop through that is going to be a new column, right? And then the function that I'm applying is this, right? So this is really what I'm doing. And then I'm saying, okay, where do I want that column to go in this function, the thing I'm looping through, right? And here I'm looping through my functions and applying each function. Okay, so another thing I could do here is I could say mapdf, and then I could say function f, right? And then I could have f with the parentheses call on the inside. And maybe that would be a little more clear. Does that help?
Yeah, that helps.
Okay. Any other thoughts? Okay, so this is a nested loop. Nested loops are gnarly, and they're hard to wrap your head around very, very easily, right? So if you get a loop inside a loop, you can sort of parse it if you really work hard, but it's complicated. And if you get a loop inside a loop inside a loop, then stop. There's better ways to do it, okay? So what I generally do when I do this is I turn one of the loops, actually the inner loop, whatever the inner loop is, into its own function, okay? So here's an example, right? I'm creating a function which I'm calling summarize call, okay? that is a function that's going to take one argument, which I'm calling column. Again, the argument is just a placeholder. I could call it X. I could call it anything, right? And then I'm just going to put my code in there that I used before to loop through a single vector to apply each of those functions within summary. Okay? So here's my new function. Now that we have this function, we can just loop that function through each column. Okay? Oh, shoot. Oh, shoot. I don't know why this didn't work. Let me look at this locally real quick. Because I know it was working locally because I checked just a second ago. This was 36. Well, I guess I'm wrong. I swear it worked just a second ago. Whatever. Okay, so basically, man, that's really frustrating. Basically, I'll go back here. We would do this exact same thing, except now we can say mapdf empty cars, and we can just put right here, we can replace all of that with summarize call. Okay? Because it's going to do that summarize call function is doing the looping. Okay? So another way we could do it, obviously, is we could do dot x, we could say summarize call dot x, right? Tilde summarize call dot x. That's really annoying to me that this thing is not working. So let me even do this real quick to see if I can get that to work. Yeah, there it is. I don't know why that didn't work. Anyway, this is now the exact same thing. Okay, we have empty cars and we're just applying this function to each column. Okay, this function does a loop, but now when we're doing this loop, we don't have to focus on that loop anymore. We're just focusing on what is the output from summarize call. So then that allows us to sort of focus on one loop at a time. Okay, questions on that? Okay, then if we wanted to, we could extend this even further and wrap the whole thing in a function. So now I have this function that I'm calling summarize df, summarize a data frame, right? It has function, takes one argument df, and it's going to map through that data frame and apply the function summarize call. Okay, and then we can go ahead and apply it to any data frame. So here I'm now testing it out on a new data frame, air quality, and I get something like this. Okay? Questions? Okay. Notice we do have missing data. Any idea why?
Probably didn't ignore the NAs and the mean and SD functions.
That's exactly right. So if we go way back to where we created that SMRY summary list, when we said mean equals mean, and that was it, right? So if we wanted to ignore this, we would have to include an additional argument, na.rm equals true. Okay? And we will get to that actually later. Okay, moving on, we're going to talk about the components of a function now. So we've kind of jumped ahead and now we're going back. Okay, so what I basically did is I showed you in R that everything is a function. And then from there, we went through a use case of when you might want to write a function, right? And I specifically showed you that in that case, you might want to loop through a list of functions to apply to a column, and then you might want to generalize that so you can loop through all the columns of a data frame, and then even from there, further generalize it so it can be applied to any data frame, okay? It actually wouldn't work for any data frame, but it would work for any data frame that has all numeric columns, okay? And we'll talk about conditions and things from there. But now we're going back because I wouldn't expect that you'd be able to write any of these functions that we just did. So that's just an example. And now we're going to dig into what the actual components of a function are, and you'll start to write your own functions. Okay, so there are 3 components to every function. Okay, they are the body of the function, which is this part. Okay, it's what comes between the curly braces. Okay, that's the body of the function. The formals, which is the arguments of the function, the arguments the function takes, and the environment. The environment is the one that we won't focus on too much because it's not hugely important for now. It is important, and we will need to talk about it, but only in a limited way. So I'm actually going to talk about that in these slides, and then in terms of lexical scoping, which I'll introduce here in a second. But then we're probably not really going to talk about it again from there unless you have a need to for your specific final project or whatever. Okay, so formals. The formals are the arguments supplied to the function. Okay, so what's one way that we can identify the formals of a function? Let's say lm or mean or whatever, any function that you can think of in R. How would you identify what the formal arguments are to that function? What's one way you could do that?
Looking at the documentation.
The help documentation. That's exactly right. That is how I would generally do this, right? I would do question mark, and then it would bring up the help documentation. And the first thing that you'll see there, actually, let's just go do it. Let me switch my screen share. Okay, so here, right, if I say question mark lm, it will bring up the help documentation. And the first thing I see here is the function here, and then all of these things, right? What's in here in the parentheses, that's the formal arguments for that function. Sometimes these formal arguments have defaults, like model equals true, method equals QR. Sometimes they do not, like formula and data, right? It just says, what do you want? Other times it doesn't have defaults, but they actually do. So like you don't have to supply subset. It's just going to be null if you don't. And then if it's null, it's going to do one thing. If it's not null, it's going to do another thing. But others like formula and data, they're going to require that you supply those arguments. Okay. So that's one way. That's the most common way. That's how we would do it most of the time. But we can also use a function to identify those arguments. So we can just say formals on lm, and it will give us a list of the formal arguments for that function. Okay. How do you see the body of a function? Well, one way to do it is just to print the function. So let me go back here again. So rather than doing question mark lm, I could just type lm and hit command enter, return. And there is the body of the function right there, right? Between the curly braces. Okay. So that's cool. But sometimes this is not really very helpful, because if I do like sum, this is the entire function. Dot primitive sum. Or like this, if I say print, that's the function. Not very helpful, right? So I think actually the best way to do this, to see the body of a function, is to find it on GitHub, right? Almost everything that's on CRAN now has a CRAN mirror repository on GitHub. So even if you have your own GitHub, once it's pushed to CRAN, CRAN takes a snapshot of it and puts it on GitHub as a mirror. Okay, so I would recommend doing that. The other thing that you can do, though, is you can hit Command or Control and then just click on it, and it will bring it up like this. So this gives you a tiny bit more information, but still not very much, right? Use method print. That's not very helpful. Okay, and that's because of this thing called S3 method. So the actual method for this is going to depend on the thing. So if I said print.lm, that's actually a different function. And I could hit command click and it doesn't work. Sometimes it works, sometimes it doesn't. Yeah, I can't find it, whatever. So anyway, that's one way that you do it. Let's see if we can go online though. Let me switch my share. And what if I just say print lm github r lm.r. Okay, so here's the lm function, and then lm.fit. Let's see if I can just search for print.lm. There it is. Okay, so this is the actual source code for what's going to happen. Not that line. Stop that. Whatever. This is the actual source code for what's going to happen when you call print on an LM object. Okay, so as you get better with functions and you get more comfortable with them, I would recommend seriously going and looking at source code like this for the functions that you're interested in. Specifically, if they're like base functions like this, it may not be all that useful, right? But if it's like some function from some package that you're using that you like, go and check out the source code for those functions, see what they're doing. If you're looking at sort of some of the tidyverse stuff, it's going to be pretty complicated too, because they're going to be really deeply nested. But for a lot of more like amateur programmers, it's not going to be nearly as difficult to track, and sort of trying to parse through that line by line is going to help you understand it a lot better. Okay, and you can do that again with like modeling stuff, right? So say you're interested in multi-level modeling and you use LME4, you can go to the source code for LME4 and actually walk through the whole code and see what's happening. Okay, again, it's going to be fairly complicated, but you can do it, and that's pretty neat, I think. Okay, you can also use body to, so body is another function to see the body of any function. All right, so the arguments, the formals, and the body, those are the two most important parts of the function. And those are the things that we'll be working with a lot as we write our own functions. The environment is much less important, but I'm going to spend a couple of minutes on it here because it's still important. Okay, it's generally not, you're not going to have to worry about it too much, but I want to show you why you would. Okay, so here I'm creating a function which I'm calling double, and it is just taking a function x and it's going to multiply that x by 2. If I call environment on double, it'll say our global env. Okay, so it's saying this object is in the global environment. Great. What about environment for LM? Well, that's in the namespace stats. Okay, so I have my global environment that I'm working in, and then I have packages that I might have loaded, right? LM is in the stats package, which is a different environment than my global environment. Okay, and that's important because of lexical scoping, which is this. Okay, so here I have x, and I'm defining that as 10. Then I have f1. This is a function that doesn't take any arguments. It has no formals, but it defines x as 20, and then it prints x. So if I call f1 here, what do you think it's going to return? Pretty much got a 50-50 chance here. What do you think?
20.
20 is correct. What about this one? Now we've got x is 10, y is 20, and we say f2, x is 1, y is 2, and we're going to sum x and y. What's f2 going to return?
Please say 30.
3.
Oh.
So it's going to return what's inside the function. All right, but the last one, this one's a little bit tricky. What about f3? Okay, so here I have x is 2, and I'm defining x3 where I say y is 1, and then it's going to sum x and y. What's that going to be?
Not 30.
Not 30, no. 3. And then when I say y, I'm going to get error. Okay, it can't find y. Y only exists within F3. Okay, but x exists outside of F3. So basically what this function is going to do is when I come to this line, sum x and y, it's going to say, okay, x, where is x? And it's going to look within the function. And it can't find it within the function. So from there, it's going to go to the global workspace, global environment, and it's going to look for something called x. It finds it in this case, and it's 2. So then it's going to add 2 to y, which it's finding within the function. And so therefore it's giving 3. When I call just y though, it can't find it because that only exists within this function. Okay, so this is environments, and this is an example of lexical scoping where it sort of starts at the smallest and then it moves out from there. Okay, so generally we won't have to worry about this too much, but if you end up with unexpected results, this could be part of why. Specifically, if you have objects in your global environment, and then you have functions that are calling those global objects, then that's fine. Like there's nothing wrong with that if it's happening just in your script. But if you're writing like an R package, then you'll want to write what are called pure functions, which means that they don't depend on anything except the inputs to those functions. Okay. All right. So this is sort of a summary of what I just said. Your functions can, and in interactive work where you're just writing an analysis script for a paper or something like that, right? They very often do depend on things that are in your working environment, right? There's nothing wrong with that whatsoever. But if you're doing that, just be aware that that's a function that I would consider a one-off, right? It's a function you're writing one time to do an operation, and you're not really ever going to use it again in any other script. You might use something that's similar to that, but you can't use the same thing over again because it's depending on something outside of the function itself. Okay? So this is a real example from a script that I wrote, and I'm not going, we're not running this function or anything. I just want to show you that this is a real example from a script I wrote where I wrote this function called extract grades, and it's going to take two objects, both of which are in my global environment. Okay, it depends on those things in my global environment, and it can't do it otherwise. So the first is diffmod. This is like a differential item functioning model, and then the items that were fit to it. And basically what it's going to do is it's going to go through this thing, and it's going to conduct some checks and transformations. And then it's going to say, okay, if the absolute value of this thing that it creates is in these ranges, 0, 1, 1.5, inf, then it's going to get this grade. So if it's between 0 and 1, it will get an A. If it's between 1 and 1.5, it'll get a B. And if it's between 1.5 and infinity, then it gets a C. Okay, and then it's returning it as a table, as a data frame, a tibble. Okay. And so this is an example where this is a super useful function because it does some transformations and takes the raw values for me and assigns letter grades to those values. But I'm only going to use this in this script. It's not ever going to exist outside of that, okay? Because it depends on these things that I've created previously in my script. Similarly, I have very often written functions to import data. Okay, so here's an example where I'm writing a function called read sub files, right? Read subject files, and it takes one argument called file, and then I'm going to read CSV that file, and then I'm going to mutate, create a new column called content area, where I'm going to extract the content area, another new column called grade, where I'm pulling the grade and making it numeric, and then I'm going to just select content area, grade, and everything, and then clean the names of the rest of the columns. And then when I do my map.df, I can just apply that read sub files. And that's sort of similar to what we looked at before when we were reading in all those I files, but I just do it through a function and then just apply that function over and over again. Okay, so again, the body of this function, like this function as a whole, I repeat a lot. But the body of this function is always going to change because it's going to depend on what the specific files look like. Okay, but that doesn't mean that it's not useful. It's super useful. And like I said, I do it all the time. It's just these are sort of more one-off functions. They're not something that I'm going to be reusing. Okay. All right. So now we're going to think about writing functions and when we might want to write functions. So this is actually sort of an example from last time. All right. We have empty cars. We're going to group by cylinder, and then we're going to nest. So we have a data frame that looks just like this. We have the sil and the data. And then we're going to mutate. We're going to create a model where I'm going to map through data, and I'm going to apply this model. Okay, so this is just a linear model where we have MPG as the outcome, and then engine displacement, horsepower, and drag ratio as the predictors. And I'm applying that for each dot x. Okay, so this is something very similar to what we've done a bunch of times. And, you know, again, if like the modeling and stuff is not clear to you, that's fine. It's really not important. The important part is that we're focusing on the looping through. Okay, so this is what we've done before. That's great. And then we talked about pulling out specific coefficients. So if we look at the first model, right, I'm saying mods model 1, I could pull the coefficients with coef m. And then if I wanted the specific coefficient, I could say coef m and then the name of that coefficient in brackets, right? So like DISP will give me this one. And then for intercept, I could do that one and it would give me the intercept, right? Whatever the name is up here, that's what would give me the return value. Okay, so that's cool. That works, that's fine. But maybe I want to write a function for this so that I can do it for all of the models. And I don't have to write complicated code like this. So what I could do is create a function, which I'm calling in this case, pull coef, right? Pull the coefficient. And so I would say the function, I'm going to pull from the model. So the model goes here, whatever the model is, right? It could be any generic model. So this is not like the previous examples where it depends on something in our global workspace. This only depends on the inputs that it's given. So we have any generic model. We're going to pull all the coefficients from that model. And then we're going to subset that atomic vector to get just the one coefficient we're interested in. So I'm saying coef name. Okay. So then I could do something like this. Okay. I'm saying intercept, DISP, HP, and drat, right? I'm going to, for each of these, I'm going to loop through model. I'm going to apply the function pull coef, and then I'm going to say what is the coefficient that I want to actually pull. And then I get each of the coefficients. Okay? Does that make intuitive sense? Even if, you know, you wouldn't feel comfortable writing that yet? Okay. So that's cool. So what we might want to do is when we do this, right, this intercept in particular is a little bit odd, right? So maybe what we would want to do is change our function. So we set the intercept as the default. So it will pull the intercept if we don't give it any arguments. And otherwise, it'll give us whatever we call. So here I say, because the intercept is generally going to be there in most models, right? So here I say coef name equals intercept. So that's the default. That's what the value will be if I don't give it any other specific value. So coef name equals intercept. Now, if I just give it the model, this value of intercept is just going to be inserted here. Okay. And so then when I take mods and I mutate and I say intercept is equal to map double model, all I have to do is say pull coef. And then that intercept will just get inserted in there because that's the default. Okay. And here's all the intercept values. Okay. We could continue to extend this. So now we say, I want to return all the coefficients. So in this case, I'm going to say coef model. So that's going to return all the coefficients. And then I'm going to return them this time instead of as a 1 by 1, I'm going to return them in a data frame. Okay. So if we look back here, when we call coef like this, right, it returns a named vector. This has the values, and then the names are each of the things that it is. So all I'm going to do basically is take the coefficients from the model, and I'm going to put them in a data frame. I'm going to say the coefficient is equal to the names of coefs, and the estimate is equal to coefs. Okay, and then I can loop that through all of my models, and I get a data frame in return, and then I could unnest those coefficients, and I get something like this. Okay, so again, this is just an example where what I'm mostly trying to do here is provide the motivation for why we would want to write functions. Because this is pretty powerful, right? In just a few lines of code, this amount of code, we have now written a function where we can apply that function to each model, and we get a data frame of the coefficients in return. And that will work for any model, regardless of the form for the linear model, right? Is that clear? Are there questions on that? Okay. Slightly nicer, we could just pull CIL and the coefs and then unnest coefs. So there they are. That's not that big of a deal though. And then we could also create a nice table. So now we unnest the coefficients and then we pivot wider, and now we end up with something like this, right? So here's all the coefficients for 4, 6, and 8 cylinders, the intercept, engine displacement, horsepower, and drag ratio. So this is just restructuring the table. All right. So I know this has been a lot, but as I said, this is mostly trying to motivate why we would want to do this. Okay. So now I want to shift focus a little bit to when would we do this? Okay. Because I think that's often a very difficult thing to do. It's like, well, okay, I could just do this. Why would I write a function? And the main reason is because you want to do some operation a bunch of times. And that's why we spent so long on looping first, is because that's the same sort of idea. You're going to take some operation that you want to do, and you're going to do it repetitively, right? If that operation is something more complicated than, say, computing a mean, then you might want to wrap that in its own function first, and then loop that function through the things that you're doing, okay? So here's an example. I'm creating a data frame here that has A, B, C, and D, okay? And it's just 10 draws from a random normal distribution with a mean of 100 and a standard deviation of 150, okay? So really wide range, but here's the 10 draws, okay, for A, B, C, and D. Now let's say I wanted to rescale each of these columns so the minimum value was 0 and the maximum value is 1. Okay, so there's lots of different linear transformations we can do, right? We can do things like z-score things. This is just another way of doing something like that, but we're just transforming these values so they have a minimum value of 0 and a maximum value of 1, and then they're going to be spaced within there according to their value. So this is how we would do it for one column. Okay, so we're doing it for A. We're redefining A. I'm saying take A and subtract the minimum value of A. Okay, and I'm removing missing data, although I don't actually have missing data, but it's good to have it in there anyway. Then I'm going to divide that by the max of A minus the min of A. Okay, that's all I'm doing. A minus the min divided by the max minus the min. That's going to rescale things so they have a minimum value of 0 and a maximum value of 1, and they're going to be spaced in there the same as they were before. So here's my new column. Okay, cool. So we could do it for all the columns like this, right? A, B, C, D. So basically all I've done is I've copied this code here and I've pasted it over and over again. And then we end up with something like this. Okay, so that's cool. What's an alternative way that we could do this without writing a function though? So if I want to do this, I have
Using map.
using map, or specifically mapdf, right? I have mapdf. I'm going to say loop through df, and then I'm just inserting .x. We could also use modify here too, but I'm just saying, I'm just putting .x in there for each column. And that's cool. That's fine, right? Another alternative, because this is still not the most complicated example. But another alternative is we could write a function. Okay, so let's think about this for a second. Look at this code, not that one. Let's look back here. Look at this code. Okay, if we were going to write a function to do this, what do you think the formal arguments would be? We want to rescale something. What's the something we want to rescale?
The column.
The column, right? Or the vector, or the whatever. So you could call it X, you could call it call, you could call it whatever, right? It's just a placeholder, but that thing is really just an atomic vector, a numeric atomic vector, okay? So what will the body of this be? If we're saying, let's just call it X for now. If X is the formal argument, what's the body of the function going to be?
That whole expression, but with X in there.
That's exactly right. This part. But we're going to replace D or B or C or A with X. Okay? And that's it. So we have this thing that we're already doing, right? We're doing it multiple times. All we're going to do is turn it into a function. Okay? So you try first. Here's the thing, right? You can actually come back here and copy this if you want the actual tibble, right? Here's how I did it for one column. So try writing a function where we have one formal argument, which I would call X or V or whatever, call. And then we're going to have this as the body of the function, but replacing A or B or C with that thing. Okay, X with our formal argument. Go ahead and try that. I'll give you 2 minutes. Okay, give me an emoji that tells me how successful you were. All right, bit of a mix. If you're not successful at this point, that's okay. As one thing I want you to remember is this is the first lecture on functions of 3, I think. And then we're going to be moving to Shiny, which is still sort of a similar sort of way of thinking. Okay. So we have time for you to get comfortable here. And then we also have a lab on functions. Okay. This is how I would probably do it, right? This is the body of the function, X minus the min of X, blah, 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 right? And then we could create our function that looks like this. So I'm calling it rescale 0, 1. You could call it whatever you wanted. But generally, we want to have good names for functions that are descriptive, right? And then I'm saying function X, and then I just put the body of my function there. Okay. Then we can test it out. So if I say rescale 0, 1 on a vector that goes 0, 5, 10, I get 0.51. Great. What about a sequence from 0 to 100 by 10? Then I get 0.1.2.3 up to 10. Okay. So there's
I have a
nothing.
question.
Yep.
How does it know to be doing this by columns? For some reason, I was assuming this was going to be doing it by rows, and I was trying to specify it to do it by columns.
Yeah, so it's because the data frame, so we would actually need to loop that. If we wanted to do it for all the columns, we would need to loop that rescale 01 function through df, because that function is only going to be rescaling any vector, right? So just like here, we're looping this through, we would just say map df, and then rescale 01, right? But what is happening here, right, is that the data frame is a list, and so each element of that list is a vector, right? So nothing is going to happen in a data frame row-wise unless you use that row-wise function. Otherwise, everything is always going to be by column because it's a list, and so each element of the list is a column. Does that help?
Yeah, I was, for some reason, my brain was like taking me into loop territory, but okay, thank you.
Yeah, so you would have to loop if you wanted to apply it to actually apply it for each column. But I was mostly trying to get you to focus on this part. Okay, so there's nothing inherently wrong with this one at all. This is great and a really nice function. But we could actually make it better. So this is kind of like the mantra for writing functions always, right? The best function is the function that does the thing that you want it to do, right? That's the best function. But we can also always be better, right? And part of being better means that it's easier to read the function. So if you come back to this 6 months from now, when you get your revise and resubmit, you can actually remember what that thing is doing, and you can see it without having to walk through it line by line and trying to dig into the function more. Okay, so one way we could make this easier to read is to remove missing data once rather than doing it every single time we're applying functions, and to not calculate things multiple times. Okay, so here is an alternative way of doing this. Rescale 01b. All right, I have function x. I'm going to create a new object in here, which I'm calling z. Okay, and that's just going to be na.omit version of x. So I'm just taking x and I'm removing whatever missing data are there. Then I'm saying, okay, what's the min of z? What's the max of z? And then this is really the body of my function from before, z minus the min of z divided by the max of z minus the min of z. Okay, and this is going to be the exact same thing that we had before, and we can even make sure by doing something like this, where I'm saying rescale, here's, actually this is just 3 values, but are these things identical? Yes. Okay, and then here I'm creating an object called rand, which is just 1,000 draws from a random normal distribution, and I'm saying rescale 01 rand and rescale 01b rand, and it's saying yes, those things are identical. Okay, so this function, I would argue, is a lot easier to read. It's a lot clearer what's going on than this, because you kind of have to work through all of this code and figure out what's going on. Whereas really for this one, you're computing some stuff, and then this is like the body of the function, which is quite a bit clearer. Okay, so final solution, this is what I was just mentioning, Chris. If we wanted to supply this to the data frame, then we just say map df on df and apply the function rescale 01 or rescale 01b, as I've done here, and then there we get it. Okay, so let's pause there, and then we'll finish up these last 11 or so slides next time before we start into any of the other new content. Okay, before we sign off, though, I want to reiterate that if you're feeling a little overwhelmed, that's okay. We have more time where we're going to be working on this stuff, and this is like a whole new way of thinking, right? It's in some ways feels a little abstract, but we're going to work on it more and more, and hopefully you'll get more comfortable with it as we go along. Okay. Any questions or things before we sign off for the day? Joe, you have a question? All right. Okay, well, I will see you on Wednesday, then we'll continue to talk about functions.
Thank you.
Yep, thanks.
Thank you.